Okay, hello everyone. Let's talk about multiplication. Multiplication is basically just repeated addition. It's actually much simpler than long addition, long multiplication rather in decimal. You can see here how it works. So the multiplicand and is shifted by the bit position of the multiplier. How does that work? Well, you see here, there's a 1 in the first position of the multiplier, so you copy the multiplicand for the first position, and then you shift the position by 1, and then you multiply with the multiplier again. Multiply by 0 becomes 0, and then you shift by 1, and you see a 1 here, so you copy the multiplicand in this position again, and then you shift once and see that there's a 1 here for the multiplier, and you copy the multiplicand again. And using these partial products that we've made, you just add the partial products and get the product. So actually, binary long multiplication is easy. Thing is, how do we do it automatically? There is also something to note here where if you have a factor of m and a factor of m bits times n bits, how large is the largest possible product? So you can see that for an m bit number, the largest number that you can represent with it is is a string of all ones that goes on for m bits. And then for an n bit number, the largest number that you can represent with it is a string of ones that is n bits. Note that this is the unsigned representation. But anyway, so a string of 1 that is n bits and a string of 1 that is m bits. So if you multiply those two things with each other, their result should be the largest possible number that an m bit number multiplied by an n bit number can ever be. So if you count the number of bits of that, that's the probable maximum width of the product. Okay, we can easily represent multiplication using array multipliers. So you can see here are specific blocks to do it. And you have a full adder and just an AND bit in the specific blocks that do it. You have the multiplicand as inputs and the multiplier as the horizontal inputs. You can see here through basic addition logic, what happens is just you AND the the value of m with the respective q. You can see here the shift by 1 is actually present in the circuit topology itself. So this is us shifting by 1 for every bit of q. And then you just AND the to m to q to see if you should add the part over here, and then the product comes out here. Well, the product comes out sequentially, so you start with this one and then this one and then this one and this one. So the product comes out like all the way here depending on the value of q. So here you can see if q equals 0 for a specific row, say q1 is 0, then this AND will be off. So this will always be 0 if q is 0 over here. So that means that the partial products on this row will all be 0. If it's 1, then the partial products in this row will be m0, m1, m2, m3. So it's basically the circuit version of what we were doing in the previous slides. You can look at this for yourself. It's quite a more complicated circuit, but it's basically something that does the multiplication sequentially. So you just shift these bits. So you just replace the topological shifting by a shifter. You can do this to reduce the area of the circuit, but basically it's still it's still a sequence of shifting and then adding and then shifting and then adding depending on the value of the multiplicand. So You can just stare at this for a bit more and pause the video if you want to try to figure out how it works. But it works in basically the same principle. Okay, the algorithm is also listed down over here, but you can basically derive the algorithm from the um, sequential circuit itself as well. So here you can see an example of how the sequential multiplication works. Basically, you have register Q to contain the multiplier, and then you have a separate register M to contain the multiplicand, which you only use to actually put in the adds, whether or not you need to add. So what you do is you look at the least significant bit of register Q. If it's 1, then you add. And then after you add, you shift it once to the right. And then you look at the least significant bit again. So rinse and repeat. This is 0, so you don't add. So after addition, you shift to the right. Well, after adding nothing, you shift to the right, and then look at this again. It says 1, so you add, and then after you add, you shift again. It says 1, so you add, and then after you add, you shift again, and then you get the final product. So for a total of 4 add and shift iterations. So one iteration goes from add and starts with an add and a shift. So the fourth iteration is an add and a shift as well, and you get the final product. For signed multiplication, actually, it's pretty easy if you have a signed multiplier and multiplicand. Um, but anyway, if the first number is negative and the second number is positive, what you do for signed multiplication is just you extend the sign bits for negative numbers. So basically here you have negative 13 times 1 for the first partial product. So you have 10011 over here, which is normal, but then you have a string of ones here all the way to the end of the products. So then you just continue that down the line. But actually, an easier way to do it is to just convert 13 to the positive 13 and you XOR the sign bits. So for example, you have XOR the sign of A and sign of B. So for example, we know that two negative numbers multiplied to each other is positive. Two positive numbers multiplied to each other is positive as well. Anything that has different sign multiplied with each other will be negative. So um, what you can just do is you convert 13 back to positive 13, that is 01101, and then you multiply that with this thing, and then you get a final answer, and then you convert that to 2's complement or leave it alone depending on the sign of the last bit. But basically you just need to take note of the ending sign and multiply the positive versions of the numbers that you multiply to each other. um there is an algorithm. Now comes a slightly exciting part where um you don't want to multiply too many partial products. So there is a way for us to reduce the number of partial products by noting that, say, a string of ones can actually be um, broken down into a 1 that comes after the string of ones minus a 1 that comes at the start of the string of ones. So you can see here, this is after the string of ones, so the next 0 after it becomes 1, and the 0 at the start of the string of ones, that is the first one of the string of ones, becomes negative 1. So you can see here, in booth notation, the expansion of this will actually be here 0 plus 1 and 3 zeros, and then a negative 1 and a 0, and this is what we use to multiply. You'll see that next. So here, so in the Booth algorithm, you can see here normal multiplication. So this is So this 0 becomes 0, and then 1, you have partial products over here, an entire string of 1s, and then zeros here as well. And the problem here is that your sums are very like you have a lot of addition operations here, because you have you're adding four different things. If you use the booth notation for this thing, where you have a positive one and a negative one instead, then the number after the string becomes positive one, and the number at the start of the string becomes negative one. And now you see here what happens. You have here this first number negated would be 1 0 1 0 0 1 1, and then you just use that as the partial product, because that's the negative of the multiplicand. And you see here we used it as a partial product, and then we just extended the sign bit to whatever bit representation that we needed for the end of the, or whatever m plus n bit representation that we needed for the end of the operation. So now that we have that, the only other non-zero partial product that we need is a plus 1. So we have here a plus 1. You can extend this with zeros if you want. But basically, what the Booth algorithm improved is you only have two things to add now instead of four. So here, you can see examples of how we recode a a boost multiplier. So there are good cases and there are bad cases for the boost multiplier. You have here a very long string of 1, so this becomes negative 1 and the positive 1 after it. End of a string of 1, so it becomes a positive 1, and the start of a string of 1s becomes negative 1. So for ordinary multipliers though, you have here, well, for typical numbers, you have here start of a string of 1s, so this becomes plus 1 and negative 1. This is a start of another string of 1s, so that's plus 1, and this is negative 1. This is a start of a string of 1s, but it's just 1, so you have a 1 here and a negative 1 here. Or alternatively, you can just keep the 1. Um, and then you have here the start of another string of 1s and the end of another string of 1s. Worst case scenario though is something I call a 5 type number. That is, it consists of repeated hex fives, basically alternating zeros and ones. There's also another thing, another type of this called that I call a 10 type, which is basically 5 times 2, but it's alternating the other way around. But basically, this is the worst case for a booth, where it translates basically into more partial operands than usual. So using booth, sign multiplication is as before. You can have it. Okay, this is the partial product. This is the first partial product. Encounter a negative 1, so you negate it, and then you encounter a positive 1, so you don't negate it, but use it as a partial product, and you encounter a negative 1 again, so here there's negative, positive, negative. Here is negative, positive, negative, and then you add that to get um, the full product. So here as well, you can have you can have a booth multiplication of a negative and a positive um, number, and you can still represent that using booth multiplication. You still also get negative um, you still also get negative 78. The thing is just that when you negate a when you negate a negative number in booth, you just use the positive equivalent. So unlike normal multiplication, you can just treat these two in the same way instead of doing the XOR stuff. But I recommend doing the XOR stuff because that's more uniform.